Hey there guys, so this is going to be our second trig video. So hopefully it helps you out for your test coming up. The unit circle and trig functions of any angle. Alright, let me get my pen going here. Oops. Sometimes it's a pain. There we go. All right, unit circle and trig functions of any angle. So this is the warm-up we did in class. Let me go ahead and go through it. You're in a helicopter 3,000 feet above the ground pursuing a stolen car. The angle of depression to the car is 23 degrees. How far from the car horizontally are you? So we need to make our picture. I'm going to say H for helicopter, C for car, right triangle. Angle of depression is always the angle from the sky down. So it's this angle, 23 degrees, and we are 3,000 feet above the ground, so 3,000 is our height. So if H is our reference angle, we are looking for X, the adjacent. We have the opposite, so that's going to be tangent of 23 degrees is opposite over adjacent. So X is whatever 3,000 divided by tangent 23 is. Type that into my calculator, and I get 7,067.6. All right. So there's our warm-up. So the definition of the unit circle, it's a circle with radius 1. So it has the equation x squared plus y squared equals 1. Should remind you kind of the Pythagorean theorem. On the graph over here, you can see the points at the x and y intercepts. So we have 1, 0, 0, 1, negative 1, 0, 0, negative 1. And remember, with trig, we start here. And our angles, positive, go around this way, negative, go around that way from the 1, 0. So 1, 0 is always where we start. So on our unit circle, we can find our 6 trig values, our 6 trig ratios. So sometimes we use t, sometimes we use theta for the angle. And then the x and y over here correspond with the points on the unit circle. So sine is y, cosine is x, tangent y over x. And then cosecant, secant, cotangent are the flipped over versions as you would expect. So the points on the unit circle, the handout I gave, essentially gives the usual points that we use. Okay, technically there's an infinite number of points on the unit circle, but obviously we can't do that. So what we do is we have the 45-degree marks. So starting at 0, 45, 90, and so on. So you'll notice a pattern here. All the corners, so like here, 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 and here, all essentially have the same xy values except for some negatives going on. Okay, there's a lot of symmetry here. And then same thing for the intercepts. Okay, it's all 1s and 0s with different negatives going on. Okay, we also do the 30-degree marks, so starting at 0, 30, 60, 90, and so on. Okay, these all have a pattern as well. Other than the intercepts, it's all just square root of 3 over 2 and 1/2. And it keeps on, flip-flopping as you go, the x and y. And there's also areas where you see symmetry, so like this point and this point have the same xy values except for negatives going on. Also, this point and this point. So all 4 of those points have the same xy values just with negatives going on. And the negatives are the usual quadrants that you're in. Similarly, we have the points, I'm going to mark them with x's, there, 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 and there. All have the same xy values going on, just with different negatives going on according to their quadrants. So you don't really have to memorize unit circle, but it is good to see all the different patterns so that you know what to expect, okay, and what kind of numbers show up and stuff like that. So the purpose of the unit circle is, for one thing, it's a reference. Okay, you have a bunch of conversions here, degrees and radians. So like 30 is the same thing as pi over 6, and then you know what your x, y values are, so your sine, cosine. And the other part of it is accuracy. So the unit circle are exact values. And a lot of what we do in trig is exact values, because the moment you have a decimal, or the moment you throw something into the calculator and you have an irrational decimal that you have to round, you lose your exact values. So if you notice on here, like what I said before, there are a lot of symmetry situations going on. All four of those have the same XY values and just negatives, positives, same as the other one. So notice your symmetry. Okay, it's very handy. Also, notice that all you have is XY values. So like if I wanted sine of pi over 6, that would be the y value, so that's right here, that's 1/2. Cosine pi over 6, that's the x value, square root of 3 over 2. There isn't a tangent listed. So square root of 3 over 2, 1/2. It's y over x, so 1/2 over square root of 3 over 2. You have to do some fraction work here. So copy dot flop times 2 over square root of 3. Cancel, cancel, 1 over square root of 3. Now we don't want to have a square root on the bottom because that's irrational. So I'm going to multiply both top and bottom by square root of 3, and I wind up with square root of 3 over 3. So the tangent usually takes some work. What I would recommend is going around the circle and doing the tangents wherever you can. Each of the 4 points I listed will have the same tangent outcome, except it's going to be positives and negatives. So here it's positive over positive, stays positive. Down here it's negative over negative, also turns positive. Up here it's positive over negative, so negative square root of 3 over 3. Down here it's negative over positive, so negative square root of 3 over 3. So just doing one set of tangents gave me 4 of the points. So you don't have to do them all, okay? Or you don't have to walk through them all. So it might be a good idea to add your tangents, is what I'm saying. All right, so I'm going to keep on coming back to this slide quite a bit, just to reference it as we go through this. So there's going to be a lot of flipping around on this slideshow. So some examples, sine, cosine, tangent for the different trig functions at each real number below. So I already did pi over 6. That was sine pi over 6 is, what was that, 1/2. Cosine pi over 6 was square root of 3 over 2. And the tangent pi over 6 was square root of 3 over 3. Okay. So B, 5 pi over 4. First of all, let's find it. 5 pi over 4 is right there. So both the x and y are negative square root of 2 over 2. So sine 5 pi over 4 is negative square root of 2 over 2. Cosine 5 pi over 4 is negative square root of 2 over 2. Tangent 5 pi over 4 is 1. Because x and y are the same, so y over x is just 1. Which, if we go back, tangent is 1 there, means it's 1 there, means it's negative 1 there, and negative 1 there. So now we've got a bunch more tangents. Okay? At t equals 0, so at 0 degrees, we are here. So 1 and 0 are x and y. So sine 0 is 0, cosine 0 is 1, tangent 0 is 0 over 1. And lastly, t equals pi. So over here at pi, which by the way, I'm going to write the tangent as 0. So over there, negative 1, 0, same thing, just negatives. So sine is 0 is 0, cosine, pi is 0, cosine of pi is 1, negative. and tangent of pi is 0 over negative 1 is 0. So those are zeros also. Okay, so I've almost added all the tangents for you just by going through those problems. And you'll be doing those tangents a lot, so you might as well have your reference. There's a couple ways that this might change up a little bit, such as this one. So the 6 trig functions for negative pi over 3. So I'm going to do sine negative pi over 3, cosine negative pi over 3, tangent negative pi over 3, cosecant negative pi over 3, secant negative pi over 3, and cotangent negative pi over 3. So my 6 trig functions. Now, if we look back at our unit circle, there are no negative degrees, but just remember that positive goes counterclockwise, negative goes clockwise. So pi over 3, so this pi over 3, if it were positive, it would be right there. But it's not positive, it's negative, so if I use symmetry, instead of going counterclockwise to there, I'm going to go the same distance clockwise. So I'm at this point now. So negative pi over 3 is the same thing as 5 pi over 3. So y is negative square root of 3 over 2, and x is 1/2. Okay. Tangent, negative square root of 3 over 2 over 1/2. So copy dot flop. Cancel, cancel. That's just negative square root of 3. No need to rationalize the denominator. Okay. So what I'm going to do is go ahead and mark my negative square root of 3 as my tangent, which means up here it's positive, over here it's negative, and down here it is positive. And cosecant, secant, cotangent are the flipped over version. So cosecant, flipped over version of sine. So negative 2 over square root of 3, which is going to become negative 2 square root of 3 over 3. We get rid of the square root on the bottom. Secant instead of 1/2 is 2 over 1, so just 2. And cotangent instead of negative square root of 3, it's going to be 1 over negative square root of 3, which turns into negative square root of 3 over 3. So that's my 6 trig functions. Okay. So remember, anytime we're using the unit circle or the problem says exact value, do not touch the calculator. Okay, the moment you touch the calculator, you get a decimal that's been rounded, and that's no good. Okay, another version where it might throw you off a little bit is this one. Evaluate the function below using coterminal angles as an aid. So 13 pi over 6 is not on the unit circle. So let's look at it. 13 pi over 6. We have pi over 6 right here. As we go around, we see some others. 5 pi over 6, 7 pi over 6, 11 pi over 6. So now we need 2 more pi over 6s. So 1, 2. So it's actually going to be pi over 6 is the same thing as 13 pi over 6. Or we can do that numerically. So coterminal, remember to use coterminal, you add or subtract a full rotation, and then you get angles that have the same measure or the same diagram. So 13 pi over 6 is too many rotations. And so we want to reduce the number of rotations down to something that is on the unit circle. So to do that, 13 pi over 6 minus 1 rotation, 2 pi. So common denominator, 13 pi over 6 minus 12 pi over 6 is pi over 6. So sine of 13 pi over 6 is equivalent to sine of pi over 6, which we've already done. It's 1/2. So if the angle is not on the unit circle, use coterminal angles, add or subtract. full rotations until you're down to something on the unit circle, something either less than 2 pi or less than 360. All right. So a couple other types of problems that may show up in terms of kind of using the unit circle. However, we're going to be outside the unit circle now. So assume that B is an angle in standard position whose terminal side contains the point -3,5. Find the degree measure of B. So -3,5 is a point over here. So that's the terminal side of the angle. This is the angle B. So we're finding the angle B. Now, the way we're going to do that is we are going to drop down a line, make a right triangle. So my right triangle has a height of 5 and a width of 3. Okay, I got that from the points. Now, this angle down here is not B. We're going to call it B prime, which is the reference angle for B. Okay, which I realized in class I didn't really discuss reference angle till the end, so I'm going to move that up on this one. So I'm going to switch around my slides a little bit. So that said, what we're doing is we're finding B or B prime, and then we're going to find B. So remember, to solve for an angle given two sides, we have opposite adjacent. So tangent of B prime equals 5/3. So B prime equals inverse tangent of 5/3. And that's going to be 59 degrees. So if this angle is 59 degrees, then the supplementary one, so the real angle, is going to be 121 degrees. Okay, so you're using your angle in standard position to find information. Okay, sometimes you'll find angle measures, sometimes you'll find trig ratios, but it all comes down to drawing a triangle using that point. Okay, so let me jump to the end real quick in regards to reference angles. So reference angle is the acute angle formed by the terminal side of a given angle and the horizontal axis. So the one we just had was a quadrant 2 angle. So if the angle is theta, the reference angle is this one right here, which is theta prime. And if you notice, they both add up to 180. So depending on what quadrant your angle is in, you just have to use some common sense for what that reference angle would be. In quadrant 2, they add up to 180. In quadrant 3, the reference angle is right here because we're always going back to the horizontal axis, the x-axis. And so in this case, theta is more than 180, and so we subtract 180 to get our theta prime. Or vice versa, if we have the reference angle, we add 180 to get the regular angle. And quadrant 4, we just complete the circle, complete the 360 or the 2 pi to get the reference angle. So like if our initial angle was 300, then the reference angle would be 60 to complete the 360. And just to give a couple more examples over here, let's say our reference angle in quadrant 2 is 200 degrees. If we subtract 180, that would make our reference angle 20. And over here in quadrant 2, let's say our initial angle is 100 degrees. That would make our reference angle 80, because it's 180. Okay, so that's what reference angle is. That's what that little mark means. So we have theta prime, or in the last case, we have B prime. So, all right, all the way back again. So that's that one. Let's go ahead and try another type of problem. Assume that A is an angle in standard position whose terminal side contains the point 1024. Find the exact value of sine A as a reduced fraction. So we have the point 1024 somewhere out here. Let's say that's the point 1024. And so, like I said, anytime you have a problem like this, you drop a line, make a triangle. And my triangle has a height of 24, since that's the y value, and a width of 10. So if this is my angle A, I want sine. But sine is opposite over hypotenuse. So I need to find the hypotenuse first. So in a lot of these problems, you have to use Pythagorean theorem. So 10 squared plus 24 squared equals, let's say, x squared. That means x equals square root 10 squared plus 24 squared. So if I plug this into the calculator and I get a decimal, then I'm going to backtrack and not use that because we want exact values. But I didn't. I got 26. So the sign of that triangle is 24 over 26, but we want a reduced fraction, so 12/13. Okay. And moving on. So as I kind of hinted back in the unit circle, different quadrants have different signs on the trig functions. So positive, negative. So since sine is the y value, okay, it's positive up top, negative down below. Since cosine is the x, it's positive on the right, negative on the left. Since tangent is a combination, when both are positive, it's positive. When both are negative, it's negative. When only one is negative, it's negative. When only one is negative down there, it's negative. So sine, up and down, cosine, left and right, tangent and cotangent, the corners. Okay, this also works for cosecant and secant, since those are flipped over version of sine and cosine. So this will be necessary for the next couple problems. Okay, in these problems, you'll be given some information. It might seem a little cryptic, and then you're going to solve for missing trig functions. This diagram will determine if they're positive or negative. So, give the exact ratios of the other 5 trigonometric functions given the sine ratio below and the fact that the terminal side is in the second quadrant. Also find the angle theta rounded to the nearest degree. So, second quadrant, and this is the information we're given. Okay, sine of 7/10. I'm not really going to draw the graph. I'm just going to draw a triangle that has a 7 and a 10. Okay, and just like the last problem, I need the width. So 7 squared plus b squared equals 10 squared. So b equals square root 10 squared minus 7 squared, which is a decimal. So I'm going to backtrack and just say, what is 10 squared minus 7 squared? And that is 51, so I'm going to leave it as square root of 51. So now that I have that, I can find my cosine theta, tangent theta, cosecant theta, which is 10/7, just flipped over what was given, secant theta, and cotangent theta. So of this triangle, let's see, cosine is square root of 51 over 10. Tangent, 7 over square root of 51. So that turns into 7 square root of 51 over over 51. We got rid of the square root on the bottom. Secant is flipped over cosine, so 10 over square root of 51, which is 10 square root of 51 over 51. And cotangent is square root of 51 over 7. So now we have all our fractions, but we haven't used the fact we're in second quadrant yet. So if I back up, second quadrant is right here. And sine is positive, cosine negative, tangent negative. So cosine negative, tangent negative, sine is positive, secant negative, cotangent negative. So the fraction gives us our triangle, use Pythagorean theorem to solve for a missing side, and then use the quadrant to figure out positive negatives. So I'm just going to show you a few more examples about how the information can look cryptic when in reality it's no different than this problem. So here's one. If tangent theta equals negative 5/4 and cosine is positive, then find sine and secant of theta. So this one's not directly telling us the quadrant, but we know that tangent is negative, cosine is positive. So if I go back Tangent negative, cosine positive. So cosine is positive on the right. Tangent is negative on the bottom right. So we're in quadrant 4. So I'm going to draw my triangle. Tangent theta is negative 5/4. So 5, 4. Find the hypotenuse. So 4 squared plus 5 squared equals c squared. So c equals square root 4 squared plus 5 squared. If it's a decimal, I'm going to backtrack. And it's a decimal, so 4 squared plus 5 squared is just 41. So the hypotenuse, 41. So the sine of this triangle is 5 over square root of 41, which is 5 square root of 41 over 41. Secant is the opposite of cosine, so cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent, so square root of 41 over 4. So in this one, just a little more cryptic on the quadrant, but you still have a fraction and a quadrant. And let's try another one. If tangent is 6/5 and sine is negative, so tangent is positive, sine is negative. Tangent, sine negative on the bottom. So which one of those tangent is positive? Bottom left. Quadrant 3. Whoops, I almost forgot to use the quadrant in this last one. So let me backtrack. Quadrant 4, sine is negative, cosine is positive, so secant's good. So I missed a negative. All right, triangle, tangent, 6/5. And third quadrant, so I need my Pythagorean theorem. 5 squared plus 6 squared. And square root of that's a decimal, so 5 squared plus 6 squared is 61, so square root 61. Okay. And we want the cosine of that, so 5 over square root of 61, which is 5 square root of 61 over 61. And in quadrant 3, the cosine is negative, because that's on the left. And let's try one more, just a slightly more cryptic way of showing you where we're at. So cosecant, 12/5, and we have this inequality over here. So first of all, the inequality tells us which half of the circle we're on, and then cosecant, positive, so sine is positive. So the inequality tells us that we are in the right half of the circle because we're between negative pi over 2 and positive pi over 2. And we want sine to be positive. And so we are on the right-hand side. Sine is positive in quadrant 1. So you just got to use the clues to figure that out. So cosecant, we have a triangle, theta, sine is opposite over hypotenuse, so cosecant, hypotenuse over opposite. I need my third side, so 12 squared minus 5 squared, and it's a decimal, so square root of 119. We want sine, cosine, and tangent. So sine, 5 over 12, cosine is square root of 119 over 12, tangent 5 over square root of 119, so 5 square root of 119 over 119. Lost my thought for a second. So there's our 3 answers. Now we are in quadrant 1, everything's positive, so they stay positive. So that's it, and that's the last bit of stuff before the first test. Make sure you're asking questions and reaching out if needed.